All right, let's continue. This time we're going to talk about acid strength. We said before that some acids are strong, some acids are weak, some compounds don't donate H plus to water. Why is that? What's the basis for that? We just sort of accepted that. We use Ka as a way of gauging whether an acid is strong or not, right? So before we go into the actual molecular explanation, let's first have some kind of basis for comparing the strengths of acids. Okay, let's calculate what we would call the Ka of hydronium ion if we were going to so that we can make a valid comparison. Okay, remember when we said what was the when we talk about the ionization of the acid. So if you have an acid HX, for example, the equilibrium constant, okay, which we call Ka, is what? It's for this reaction. HX plus water gives you H3O plus X minus, right? So the extent to which this reaction occurs, the equilibrium constant for that is called Ka. So we use that as a basis for determining acid strength. The larger the Ka, the farther this goes forward, right? And we said that for strong acids, that number is really large. In fact, for HCl, okay, that's at least 10 to the 6th. So just for comparison, so we can make a basis for comparison. Let's calculate what Ka for H3O plus is going to be. If I have H3O plus, I react that with water, okay, it will have to it will transfer a proton to water. What will I get? I get H3O plus again, and I get water again, right? Now, you might say KEQ for this should be 1. That's correct, but if you want to compare it with the other acid, let's pretend that this H3O plus is actually H plus H2O. So your H2O is your X, okay? So we're going to treat this H2O as though it was X. So we're going to use concentration of H2O instead of the activity of 1, okay? Just so we can compare the Ka. And if we did that, okay, so your Ka then you would say is H3O plus times H2O divided by H3O plus. So H3O plus concentration is just going to cancel out. So the Ka of the hydronium ion is just the concentration of water for comparison purposes. And that's 55. Where did I get that number? Concentration of water. Moles of water over volume of the solution, which is just going to be the volume of water, right? Okay, if I have a mole of water, how much volume does it occupy? A mole of water is how many grams? 18 grams. Okay, and how many mils does an 18-gram sample of water occupy? What's the density of water? 1 gram per mil, so 1 mil per gram, right? Is the volume per gram. So what is 1 over 18? And let's change this to liters because we want to do moles per liter. So times 1 liter over 1,000 mils. So that ends up being 1,000 over 18 moles per liter. What's 1,000 divided by 18? $55, right? So we say that the concentration of water in water is 55 moles per liter. Okay, so just for comparison purposes, we can say then with the other acids, we say, put on the same scale, hydronium ion is going to have a Ka of 55. So anything that has a Ka of 55 is what you would call a strong acid. Okay? Now, what would be the Ka of water itself? Well, you'd say that for comparison purposes, you're going to say water plus water. You proton transfer, you have H. So let's think of water here as HOH. Okay? So HOH. This is our X. Okay? So that gives you H3O plus. So that proton drops onto that water molecule plus hydroxide. You might say, that's Kw. Yeah, it's Kw. The KEQ for that is Kw. But like I said, compared with the other acids, we're going to treat this as though this is X minus. Okay? So that's your X minus. So Ka then would be hydronium times hydroxide, which is X minus, over this water right here, okay? So you do know that in water, hydronium times hydroxide is 10 to the negative 14, right? That's hydronium times hydroxide. And the concentration of water, we just figured that out, is 55. So that gives you 1.8 times 10 to the negative 16. Okay? Note that that is a very small number, right? We say water is a very weak acid. Okay, it has a low tendency to transfer proton. Hydronium is much stronger acid than water, right? In fact, hydronium, we say, is the strongest acid that can exist in water. Any other acid that's stronger than hydronium, like HCl, is just going to give up its proton right away. Because there's so many water molecules there that can pick up that proton to give you hydronium ion. Okay, so anything, so if you have a species, for that to be able to yield H plus in water or hydronium ions in water, it must be a better proton donor than water. So what we call weak acids are those acids that have a Ka larger than 1.8 times 10 to the negative 16. They're better than water. The strong acids are better than hydronium. Okay, so you can use, on the Ka scale, you can use these numbers as a gauge whether it's something's a weak acid or a strong acid. Higher than 55, strong acid. Higher than 1.8 times 10 to the negative 16, that would be a weak acid. Below 1.8 times 10 to the negative 16, like ammonia, for example, okay? If ammonia were to donate a proton to water, that will give you the amide ion plus hydronium. The Ka for this is extremely small. Ka is less than that for water. So ammonia doesn't give you an acidic solution. In fact, what ammonia does, it rather takes proton away from water instead. Okay? So what makes a proton donor then? Your book gives you, and most freshman chemistry textbooks give you explanations based on electronegativity and bond strength. Okay? And I'm not really comfortable with those explanations because it works one way, but it doesn't work another way. So for a particular series, they would use electronegativity. For another series, they would use bond strength. But then if you use the bond strength argument to the other series, it doesn't work. Okay, so I've looked around to find an explanation that I'm more comfortable with. So this is the explanation that I prefer, and this is something that will serve you well when you go on to organic chemistry, because this is how they actually explain acid strengths in organic chemistry. If you have a more stable conjugate base, okay, you look at the conjugate base. If you want to compare strengths of acids, compare the conjugate base. What did we know about the conjugate acid-base pair? Remember, Ka times Kb is 10 to the negative 14, right? The stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. So compare the conjugate bases, because those are once you get those compared, then you can predict what the comparison is for the acid. Okay. In general, okay, if you can look at the structure of your conjugate base and see that it is more stable, the more stable your conjugate base is, okay, the weaker that base is. What that means is it's less likely to hold on to a proton. It would rather be by itself. It has a greater tendency of just being by itself because it's more stable. So it has lesser tendency to accept a proton. Okay? So a more stable conjugate base gives you a weaker base. It will have a stronger conjugate acid. Okay. So let's take a look at an example. What we need to look at to determine the stability of the conjugate base. Most bases, as you realize, are negatively charged, right? So basically, the lower the charge density, in other words, the more spread out that charge is. So you're literally looking at a charge to size ratio. Okay? So the lower that charge to size ratio is, the more spread out the charge is, the greater the charge dispersal is, the more stable the base. That sort of makes sense because you don't want to cram all of those charged particles in a smaller volume. The more spread out they are, you have a more stable base, and you'll get a lower Kb. Okay, lower Kb, it's a weaker base. So let's compare fluoride, chloride, bromide, and iodide. Which of these is most stable? What do you know about the trend in size? They all have negative charge, right? So as far as charge is concerned, it's the same. Going down a column in a periodic table, what happens to the signs? As you go from fluoride, chloride, bromide, iodide, increases, right? So what happens to the charge density? You're getting bigger size, the charge is more spread out, you have a greater charge density, lower charge density. So which one has the lowest charge density? Iodide has the lowest charge density, right? So which of these bases is the most stable? The one with the lower charge density. So iodide is. Okay? So which one is the strongest acid? Let's see if you remember. Clicker question. Which of the acids would be the strongest? HF, HCl, HBr, or HI? This is A, B, C, D, okay? One more answer. HF is A, HCl is B, HBr is C, HI is D. Which one is the strongest of these acids? Okay. D. Okay, lower Kb means what? Most stable means weakest base, right? And the weakest base will have the strongest conjugate acid, so HI. Okay, so in terms of acid strength, HI is the strongest. Which one's the weakest? HF. In fact, what do we know about HCl, HBr, and HI? There are 3 of the 6 strong acids, right? 3 of the 6 known strong acids are HCl, HBr, and HI. Now, HI is stronger than HBr, but if you put them in water, it doesn't matter because they're all 3, HCl, HBr, and HI, are stronger than hydronium. Okay, so hydronium is the strongest acid that can exist in water. So anything that's stronger than hydronium will just immediately ionize and will donate a proton to water to give you hydronium. This is known as the leveling effect. So you can't tell in water whether HCl, HBr, or HI is stronger because they're all strong. Okay, it's like saying, you need to lift, let's say, a piece of stone. Okay, so if you're all strong enough to lift the stone, I can't tell which one of you is stronger, right? Even though you might have 3 people, different strengths, but if I ask all of you to lift up this pen, you can all lift the pen, so I can't tell which of you is stronger. Okay, so same idea in the case of the leveling effect. Hydronium is the strongest acid in water, so anything stronger than hydronium will be a strong acid in water. HF, it turns out, is a weak acid. Okay. Now, your textbook explanation for that has to do with acid strength. They say that HI is the weakest bond strength. Okay. The bond between HI is the easiest to break. Okay, and that would be a consequence of it being the stronger acid. Okay, and one possible explanation for that is the distance between H and I are much farther away. But then if you look at this, you'll see that iodide, remember, fluorine is the most electronegative, right? So fluorine, HF is the most polar bond. By the way, one thing that you do need for a proton to be able to come off a molecule is the bond has to be polar. Okay, so in explaining the trend from, for example, NH3, H2O, and HF, okay, the explanation given by your book is that HF is the most polar bond, so it's the it's the most electronegative, it's the most polar bond, so it's the strongest of the acids here. So HF is stronger than H2O. But then it turns around, going back down here, it doesn't use electronegativity. HF is still the most polar bond, but it doesn't say that HF is a stronger acid than HCl or HBr or HI, okay? Because it's not. So it doesn't use that explanation for that. So I'd rather not use that explanation. But if you see, you just need to be aware of that, because that seems to be prevalent. Okay, let's look at oxide, hydroxide, and water. Which of these has the least charge density? The more dispersed charge. If you look at these, hydrogen doesn't really make much difference in terms of size, right? So the size are almost the same. So which one has the most charge density? You need charge to size ratio, right? Or let's answer this question. Which has the least charge density? Let's see. Charge density is charge to size ratio. They're all about the same size. Which has the least charge density? Okay. Water, right? This is -2, -1, 0. Okay. Divided by the same size, more or less the same size. Water has the least charge density, right? So water has the least charge density. So since it has the least charge density among these three, which species has the strongest conjugate acid? The least charge density means that's the most stable, right? That's the most stable base. So that means it's the weakest base. So which of these three has the strongest conjugate acid? What are the conjugate acids for this? What's the conjugate acid for oxide? It's going to be one more H and one charge higher. So hydroxide, right? What's the conjugate acid for hydroxide? One more H, one charge higher, so that's H2O. What's the conjugate base of water? Hydronium. So of these three conjugate acids, which one is the strongest? A, B, or C? Ready? It should be a no-brainer, even if you didn't know the arguments behind it, right? What's the strongest acid of these three? Hydronium. Very good. Okay? So you can see the explanation there works. Water, among these three, has the least charge density. It's the most stable base. It is the weakest base. And since it's the weakest base, its conjugate acid among these three would be the strongest. So which one is a better proton acceptor? Hydroxide or H2O? A or B? Which one is a better proton acceptor? What's proton accepting called? Being acidic or being basic? Okay, so the correct answer. This is essentially asking which one's a better base, right? Which one's a stronger base? And a stronger base would be hydroxide. The least stable base is the one that's more likely to accept a proton. Okay, so which one's the better proton donor? Hydroxide or H2O? Okay, better proton donor would be H2O. Very good. Okay, now comment about leveling effect. Again, hydroxide is the strongest base that can exist in water. Okay, so anytime you have something like oxide, We said oxide is a stronger base than hydroxide. So what happens in water, there's so many water molecules there. And so what happens to your hydroxide is just it picks up a proton right away and gives you hydroxide ions. So anytime you put oxide in water, it immediately converts into hydroxide. The strongest base that can exist in water would be your hydroxide. Okay? What's the Kb of hydroxide? That's going to be what? Kw divided by the Ka of, what's the conjugate acid of hydroxide? Water, right? Hydroxide, the conjugate acid, one more proton, would be H2O. So it's 10 to the negative 14. What was the Ka of water? Go back. Ka of water is Kw over 55, right? So 10 to the negative 14 over 55. So the Kb of hydroxide is 55. So the Ka of the strongest acid in water is 55. The Kb of the strongest base in water is also 55. Okay? The Ka of water is 10 to the negative 14 over 55. All right. So let's try these. You have HPO phosphate, HPO4 2 minus, H2PO4 negative. Okay? They only differ in one. They differ in charge and they differ in the number of hydrogens, right? But the size should be more or less the same because your hydrogen doesn't make much difference in terms of size. So which of these has the smallest Kb? A, B, or C? Smallest Kb. Smallest Kb means weakest base. And weakest base means most stable base. Most stable base means most charge dispersal, right? Or lowest charge density. Lowest charge density would be, very good. How about the next one? Which of these is the largest Ka? So largest Ka means the strongest acid, right? Which one is the largest Ka? Largest Ka would be the conjugate with the of the weakest base, right? Very good. Okay, so this is the conjugate base of it. That's why in the stepwise ionization, if you have H3PO4 gives you H plus H2PO4 minus, and then you have H2PO4 minus gives you H plus HPO4 negative 2, and HPO4 negative 2 gives you H plus phosphate. Okay, what are the KQs for this? K1, Ka1, Ka2, and Ka3. Generally, what you find is Ka1 is typically much larger than Ka2, much larger than Ka3. Okay, and I think I gave you numbers for phosphate pKs earlier. Let me see. Right here, silver phosphate. 2.15, 7.2, and 12.35. Okay, so you can see K1 and K1 is much larger. K1 is 10 to the negative 2.15. That's much larger than 10 to the negative 7.2. Much larger than 10 to the negative 12.35. Okay, so in the stepwise ionization constants of a polyprotic acid, they usually decrease a lot from one step to the next. Which one's a stronger acid, A or B? HBRO or HBRO2? What's HBRO? This is BRO minus. This is the bonding here. Okay. And this is HOBRO2. So, oh, there's no O here. Okay. HOBR. Right there. And how do you complete this structure right here? How do you draw the structure of BRO2 minus? You remember? BRO2 minus. How many valence electrons do we need to show? Bromine should give you 7, right? Oxygen gives you 6. 6 times 2, that's 12. And the negative 1 gives you an extra 1. So 7 plus 12 plus 1, that gives you 20. 20 valence electrons. So what do? I try to do an octet around each one. That gives me 16, right? 8 on this side, 8 on that side, so 18, 20. Okay, so that would be that takes care of the 20, but let's look at formal charges. What's the formal charge for bromine here? This is the charge of -1. What's the formal charge of bromine? How many does it appear to own here? That's 2. Okay. 2, 4, 6, 8, half of 8, 2, 4, 2 lone pairs it owns, and then half of the 2 pairs would be 2 singles, so it appears to own 6. By itself, it would have 7, right? 7 minus 6 is plus 1, so you can lower that formal charge by putting one of these lone pairs in, so HBRO2 would have this structure right here. Okay. So anyway, which one's the stronger acid, HBRO or HBRO2? A or B? You compare the bases, right? The bases are both negatively charged. They have -1 charge. Same charge, so you look at the size to do the charge density. Which one has a smaller charge density? Okay. So let's see. Very good. HBRO2. Okay. This is larger, smaller charge density. So BRO2 minus would be the weaker base. The more stable base. The weaker base, its conjugate would be a stronger acid. A good way to remember this trend right here. So you say HBRO is going to be weaker than HBRO2. It's going to be weaker than HBRO3. It's going to be weaker than HBRO4. A good way to remember this is to just remember that HClO4 is one of the 6 strong acids, perchloric acid. So, and all the other acids then, so HClO then you would expect is weak, right? So it's weaker than HClO4. Did I mark this one? I didn't mark it, right? So explain why HOI is weaker than HOCl. Okay, HOI versus HOCl. So let's compare then OI negative versus OCl negative. It's both negative. They're both negatively have a charge of -1. Which one has a greater charge dispersal? Or lower charge density? You'd think iodide is bigger, right? Bigger size. Right? So you'd think it'd be more dispersed. And so you might think that this would be a more stable base, right? And so HOI would be a stronger acid. Right? But HOI is a weaker acid than HOCl. Did we just get into a contradiction here? we just did, but there's a way out of this. You can still use the charge density argument here in the fact that the bond between oxygen and iodine is and oxygen versus chlorine bond are polar, right? Which one's more electronegative? Chlorine or oxygen is more electronegative than chlorine. Chlorine is more electronegative than iodine, right? So this bond right here, okay, is one more polar. Bigger difference in electronegativity between oxygen and iodine. This is less polar. Where is the polarity directed at? Towards the oxygen. Oxygen is more electronegative. So we can say in a sense that because this bond is more polar, okay, we can say that the charge is concentrated more in oxygen. Because that bond is more polar. So in a way, you have a higher charge density on the oxygen, which would make more impact on the ability of your molecule to lose a proton, because now you would say that this would explain the opposite effect, the opposite observation, right? So charge is more concentrated in the oxygen, so this would be the less stable base. And this would make it the weaker base, and that would give it the stronger conjugate acid. Okay? So that would be the explanation for that. Now, the textbook explanation for this is your chlorine makes your oxygen pull the electrons even more than the iodine does. I'm not really happy with that explanation. Okay. Electronegativity. Okay, this is the typical textbook explanation for electronegativity. You say that if you compare CH4, NH3, H2O, and HF going to the right, okay, you have increasing acid strength, right? And remember we said if you want to compare acid strength, it's just the best to compare the basicity of the conjugate bases. But this, the textbook explanation for this is this: F is the most electronegative, okay? And so it's the one that likes to hug its electrons more. So that's the one that's more likely to give up the proton, okay? But then, like I said, that trend doesn't work if you explain that, if you use that to explain HCl, HBr, HI. Why isn't the trend that way? Why isn't HF stronger than HCl? So the textbook uses bond strength as the explanation for that. But if you look at the bond strengths here, that again, you get contradictory explanations, okay? So let's use the idea of charge density to explain this then. What can you do with charge density? Let's compare NH2 minus versus hydroxide. Okay, why is NH3 a weaker acid than H2O? Why is water a better proton donor? You compare NH2 minus and hydroxide. Which one would be stronger? Stronger base. Well, if you look at this, let's compare the charge density. NH2 versus hydroxide. Same charge, right? What about size? What's the trend going from left to right? Size decreases, right? So you would think water is hydroxide would be a smaller ion, and so if that's the case, then if it's a smaller ion, what do you see? It would have a higher charge density, right? It would be a less stable base. It's going to be a stronger base. That's the opposite. Okay. But if you just go by that trend, but that is not necessarily true. I haven't looked up the numbers for this, but I have looked up OH minus versus fluoride. You would think that fluoride is smaller than OH minus. In fact, it's the other way around. is hydroxide. Okay, the radius of fluorine is about 120 picometers. The ionic radius of fluorine is about 120 picometers. The effective ionic radius of hydroxide is only around 110 picometers. Okay, based on the papers I've read on this. So the hydroxide is actually smaller than fluoride. So fluoride would still have a higher, the charge density argument will still work here. This has the highest charge density. Okay. So it has the highest charge density. It's going to be the highest charge density. It would be the least stable and the most basic. Oh, that's not the other one. No, this is bigger. Okay. 120, sorry. This will have, it's the biggest, so it has the least charge density. It will be the most stable, okay? So fluoride, okay, here. Let's make that. Fluoride is the largest size. Okay, so it will have the smallest charge density. Right? And so it's going to be the most stable base. And it's going to be the weakest base. And it's going to have the strongest conjugate acid. Okay, so HF is the strongest of the conjugate acids here. HF would be the most acidic. Okay, so that explanation of using charge density still works. Okay. Kb of hydroxide, if you recall, is 55. Kb of water is 1.8 times 10 to the negative 6. So let's look at your basicity scale here. The most basic species in water is hydroxide. Kb is 55, so this is the most basic. And the most acidic is H2O. I mean, not H2O. The most acidic is H3O plus, right? And Ka of H3O plus is 55. Conjugate base of H3O plus is H2O. Conjugate of hydroxide is water. Okay, Kb is 55. How does the Kb of nitrate compare to hydroxide and water? Nitrate, where will I find this? Am I going to find it here, here, or here? Kb of nitrate. So this is 1.8 times 10 to the negative 16 right here. So A is much weaker than water. Okay, B is a weak base. Right? Over C here, higher than 55 would be a strong base, right? Where would you find nitrate on this scale? A, B, or C? Nitrate would be, do you remember nitrate? It's a conjugate of what? HNO3. What do you know about HNO3? One of the strong acids. So where would HNO3 be on this scale? More acidic than H3O plus, right? HNO3 right here would be more acidic than hydronium. So where would nitrate be? Nitrate is not even going to be a base in water, right? Conjugates of strong acids are not going to hydrolyze. They're not going to react with water to give you hydroxide because they're very, very, very weak. Okay? So here you have increasing acid strength over here. More acidic that way. Going down this way, you're becoming more basic, the conjugate base. Okay, how about, so the answer to that, nitrate's going to be in section A, right here. How about bicarbonate? HCO3 minus. Where would you find it? A, B, or C? The Kb. Carbonic acid is the conjugate acid. Okay. Right in the middle. Okay. Let's see. Let me make a better summary, a better picture here. Okay. So you have your acid strength. Yeah? You have stronger acid. The strongest in water is what? Hydronium. Okay. And the weakest acid in water is H2O. Okay. So you have here your strong acid. Here you have your weak acid. Okay. Here you have your non-acid. Right? Conjugate base would be what? Conjugate base of water is hydroxide, and the conjugate base of hydronium is H2O. So going this way, you have stronger base, right? So here you have your strong base, right? Here you have your weak base, and this is your non-base. Non-basic. Okay? So where would oxide fall in this scale? Oxide. Oxygen with 2 negative. Where would you find that? Are you going to find that in A, B, or C? Where would you find oxide on this scale? Is it stronger than hydroxide? Is it weaker than hydroxide but stronger than water? Or is it weaker than water? Hydroxide, we just talked about that earlier, is stronger than hydroxide. So you don't get any hydroxide. You don't get any oxides in water, right? So oxide is going to fall over here. Stronger than hydroxide. Okay, hydroxide is the strongest base that can exist in water. So if I told you I put potassium oxide in water, what would happen to it? Your oxide will immediately pick up protons from water. It will give you potassium hydroxide. Okay, so this is your balance equation. Metal oxide plus water gives you metal hydroxide. Okay, and that's it.